Yes.
Alright, great. So I'm talking about trace estimation through spectral methods. I originally had a longer title, but it was too verbose, so there we go. It's also actually May 20th over in Australia. Anyway, so we've talked a lot about this problem today, but briefly I'm interested in the idea of if you have a large matrix A and you have some function f, you might want to find the diagonal f of A, or you might want to find the trace of f of A. And some examples that we've seen today are a inverse, or a to the k, or the exponential of a, or log a. Alright, so there's all these different applications that you might have. These days I'm interested in finding the Kirchhoff index, which is useful for calculating centrality in graph analytics. So if you have a graph Laplacian and you take the pseudo inverse and you look at the trace, that gives you the Kirchhoff index. Alright, so generally speaking, for very large matrices, exact methods are not feasible, so we have to resort to statistical approaches. So we've heard a lot about Hutchinson's today, so I won't really belabor that too much. And if your matrix is a black box or it doesn't have any structure, that's the best that you can do. On the other hand, your matrix may have some structure that you would like to exploit. So Andreas has already talked earlier today about probing, but briefly, the idea behind probing is that you have some approximation to f of a. In the case of probing, normally it's the Neumann series, and this approximation is sparse, and you hope that this approximation is going to take into account the largest elements of f of a. So then really what you're doing with probing is you're throwing out part of your matrix, and you hope you're throwing out the smallest elements, because those are the elements that are going to contribute to your error. Alright. So some issues with this is that the Neumann series may converge slowly to f of a, so I'm going to show some results for social networks, and those social networks, the graph Laplacian doesn't converge very quickly, or the Neumann series approximation doesn't converge very quickly to the pseudo inverse. And the other issue here is that the quality of your coloring can be hard to analyze. So Andreas was talking about his method today, and he was saying that it was very difficult to find the actual chromatic number of a graph, and he's working with very regular graphs. So if you then get to social networks, your hope of finding the optimal coloring is essentially nothing. So it can be difficult to analyze the quality of your results. So based on this, going in the direction of the main observation here is that you want to find groups of nodes of f of a that have very weak connections, which is sort of the opposite of what you normally do with spectral clustering, but that's all right. We can look at the other side of the spectrum. So generally speaking, that's the main idea of my algorithm today. We're going to cluster nodes that are far apart, not close together, and we're going to try and use more direct information about f of a instead of the Neumann series. So one approach that you could take is clustering by effective resistance. That's a popular choice. So you can cluster nodes that are close in this metric, but instead we're going to look at nodes that are far apart. So how are we going to do that? We're going to look at the eigenvectors of the pseudo inverse. We're going to find two colors, and then we're going to continue recursively. So obviously there's some issues in doing that, which I'll get to here. So just to sort of motivate this idea just a little bit more, you can show that the pseudo inverse is a kernel matrix of your node vectors mapped into a space that preserves their commute time, or equivalently that preserves their effective resistance. And you can see that by just doing some simple algebra. So if you do the eigendecomposition of your matrix and rewrite it like this, you end up with a kernel matrix. So it makes sense to do some clustering. So there's one problem here, is that for large graphs, commute time is known to be degenerate, so it just ends up being the sum of the reciprocals of the degrees. It doesn't contain any information about the structure of your graph. So there's several ways people have taken to try and get interesting information out of the effective resistance. One way is just to normalize the Laplacian, which is the approach I took, and then you can show using the same algebra that this is still a kernel matrix, so it makes sense to start doing your clustering. And we're going to do this doing spectral clustering, which has nice bounds on how well you're doing based on the Cheeger bounds. All right, so when we start off with the normalized pseudo-inverse, it's easy to see how to proceed, right? You can easily get the eigenvectors. But when we recur, it's not easy to see how we can get the eigenvectors of the subblocks of this matrix. So that's really what my algorithm is about, is how do you get the eigenvectors of the subblock of this matrix. All right, so if you happen to have a good linear solver, you can make the following observation. So if you have the incidence matrix, and you have some vector, taking the norm of the vector in this matrix gives you an inner product. If you do a Johnson-Lindenstrauss projection, you can get this to accuracy of 1 plus or minus epsilon. So you can sort of get an approximation to your inverse that you can work with, and you have nice bounds with by doing this projection. And if you have a fast linear solver, you can show that this can be performed very efficiently, and then it turns out you don't need to solve this very accurately. So let's talk about how inaccurately don't you need to solve this. All right, so you have the some epsilon that controls how accurate your Johnson-Lindenstrauss projection is, and then based on that gives you the accuracy that you need to solve your linear solver. So the real question is, what is the accuracy of your Johnson-Lindenstrauss? So obviously Johnson-Lindenstrauss doesn't converge any faster than Hutchinson's, so just using Johnson-Lindenstrauss isn't going to be enough. So the main observation here is that we don't care about the accuracy of our approximation. We care about the accuracy of the ordering of our approximation, so to speak. So when you have probing, you're essentially throwing out the half, and you're doing two colors. You're throwing out what you think are the half of your matrix elements that are the smallest. So as long as you're preserving most of the relative ordering of your elements, you're going to get good probing vectors. So how large epsilon can be depends on what structure you have for your graph. So let's look at two models here. So if you have a structure where all the elements are about the same size, you throw out half the elements, and then you do two vectors, you really haven't improved you haven't improved over doing two samples of random noise. On the other hand, if you have this nice linear structure and you throw out the largest elements, you're left with a large reduction in terms of the total volume or total variance of your remaining matrix. So to get back to the idea of how much epsilon is enough, or is too much, so to speak, you have the ordering of your elements, and if you do Johnson-Lindenstrauss and you permute that ordering, in the worst case, you're going to have around your epsilon neighborhood, you're going to have these larger nodes, which should be thrown out, are going to flip and be on the side of the smaller nodes, and the small nodes are going to all flip and be on the side of the larger nodes. So that would be the worst case. So the worst case error you're going to make is you include this in your estimate, and you subtract what you're actually going to have. So you can show that this doesn't really impact the amount of variance that you get too much, even for large epsilons. All right, so as I said before, if your elements are constant size, then you really see no improvement. If your elements follow a linear model, then you're converging at 1 over s instead of 1 over square root of s. And if you have some perturbation of your elements from due to the Johnson-Lindenstrauss, you don't get very far away from your original 1 over s. So you stay close to what your original variance reduction would be before the permutation. All right, so what is the cost of doing all this? It's kind of hard to dilute this down to one slide, but just to give some flavor here, there's 2 ways you can sort of look at this. There's the sort of the complexity of the algorithm, or you can look at it as I'm going to do some number of linear solves to build up this Johnson-Lindenstrauss, and that's going to come away from my complete budget of linear solves that I do for my trace estimation. So in the first case here, you've got the cost of the Johnson-Lindenstrauss, and then for every level of coloring, you have to sort your eigenvector, and then you've got the cost of obtaining the eigenvector, and I've hidden some spectral information here in this constant. On the other hand, if you just care about the number of solves, you've got the number of solves that you're going to do for the Johnson-Lindenstrauss. You've got your total number of solves, and then because you're solving to accuracy delta, which again is based on epsilon, which is going to be less accurate, presumably, than your regular solves. These solves cost less, so you're doing some number of solves, but they're cheaper to build up this probing information. All right, how am I doing on time? All right, so I've just hit some experimental results briefly here. So here is a large preferential attachment graph. I think this was about 10k elements. I kept it small so I could invert it directly. Here I've got the actual variance you would observe, the number of vectors, and these circles are the statistical approach, Hutchinson's. These pluses are probing, so probing doesn't work well for this matrix up until you get complete coloring, so every element gets its own color. The Neumann series just converges slowly. The red squares are Laplacian, so the unscaled commute time, the degenerate commute time, as we expected, that does not perform well. And then the red and blue dots are my algorithm with different epsilons, and you can see that we're doing better than the statistical after we get going. So this doesn't include the cost of doing the Johnson-Lindenstrauss solves. So got some results here where I take that into account. So these are results that take the full cost of doing my pre-computation into account. Here's another random preferential attachment graph, again small so I could invert the whole thing. And you can see that there's some cost to doing my method, and then after a while it starts to be worth it. For a real social network, Wikivote, got it off the Florida or the Texas matrix library, sparse matrix library. Same sort of idea. First, there's the startup cost, and then as you go along, it starts to become worth it. Another social network. Again, same idea. It starts to be worth it after a while. And none of these graphs are appropriate for classical probing. Classical probing doesn't work well on these. All right, so those were all small graphs that I could invert directly. Here's a sort of a larger graph that I had to sort of look at implicitly. And here's the actual trace. The red is Hutchinson, and the blue is sort of my method. And this again includes the cost of doing my setup and pre-computation and all that. And so you can see that sort of the mean of my approach is closer to the actual trace overall, and the variance is smaller, and so on. All right, so I guess just to sum up here, since I'm about out of time, improvements over probing and statistical for some difficult problems for things that don't work well with classical probing, and sort of the other thing